Hi, everybody. How are you? How are you all? Good? Are you still alive? It's been a long day. Yeah? Because I'm going to talk about serious stuff here, so yeah, you'd better I hope you brought some sugar with you, because you're going to need it. Okay, so let's start. Shall we start? I didn't hear you. I didn't hear you. Woo! Good, that's better. Cool. Do you see my stuff? Yeah, you see my stuff. Cool. So today I'm going to speak to you about neural networks and machine learning and how we can use that to build intelligent Angular applications. First off, about me, I'm Carmen. I'm Carmen Popoviciu on Twitter, so say hellos to me there. I'm a software engineer. I do Angular, and since recently I've become very passionate about neural nets and machine learning, and this is why I came here today, because I really want to share my passion with you. I'm really excited about this stuff. I can talk on for hours about it. I can't do it now here, like I only have 25 minutes, but pick me up afterwards, let's grab a beer, and we can talk more about it. A few heads up about this talk. I really want to make sure that everybody gets to the same level, so I really want to do the intro into what a neural net is, how a neural net learns, what does it mean that a neural net is learning, and then how we can use neural nets and machine learning in Angular applications or just web apps in general. So this is my main focus for today. Cool, so let's get started. Let's talk about neural nets. What is a neural net? This is my favorite definition of them all, because I'm very excited about this stuff. So it's it says that it's the most beautiful programming paradigm ever invented. And you can see that I like it because there's a small ASCII heart there. So this is my personal favorite. But leaving joke aside, neural nets are actually just an abstraction of the human brain. And they're actually really inspired by this. They're inspired, they try to mimic how the human brain works, how the neurons connect to each other and how these signals are transmitted across. And it does this by learning from observational data. So you feed it some data, and then the net will learn by itself, and then it's going to provide solutions to your problems, which is great. So how does a neuron look like? I'm no biologist or doctor by any means. So I just Googled, and I give you the picture of the neuron. But what is important to remember is the dendrites, which are the inputs of the neuron, and then the electrical signal is going to flow out from the neuron through the axon, and then this signal is going to be carried out to other neurons, which are connected to the neuron, this one. But this is very important to remember, because when we abstract that to this, we get the artificial neuron. And the artificial neuron, just like the biological one, has inputs. And then these inputs have some weights associated to it. And the weights actually tell us how important the input is for that particular neuron. The neuron has a bias, which works kind of like a threshold. So it tells the neuron, OK, so if the sum of the inputs is greater than this threshold, then I want you to activate this neuron. Otherwise, the neuron is just going to be inert, and it's not going to do anything, in theory. And then on top of that, the inner workings of the neuron is, it's going to take all these inputs and their associated weights. It's going to do the dot product of them. It's going to add the bias. It's going to wrap that and pass it into what we call an activation function. So this is the function that activates the neuron. And it's going to give us an output of the neuron. Make sense? Cool, very good. It better be, because I worked very hard on these images. So the most basic and simplest neuron of them all is the perceptron. And the perceptron is, it's pretty straightforward, because it takes as an activation function a linear function. So what it does is going to output either 0 or 1, right? The inputs are also going to be zeros and ones, and the weights are just going to be defined by, basically by you, by the developer. So they're just random numbers between 0 and 1. But that's the perceptron. And then there's a variation of this, which is the sigmoid neuron, which gets a bit more complicated. because instead of having the linear activation function, it's going to have the sigmoid activation function. And what this does is it covers the cases when you don't want your neuron to output just 0 and 1, but you would want it to output something between zeros and ones. And this is where the sigmoid neuron comes into play. And there are different types of activation functions, but these are the most simple and basic ones. And we're going to start off with these because it's already quite complicated as it is. Cool. So how does it all come together? You have the neural net. Remember I told you about the dendrites that are very important. So you have the incoming signals that go through the dendrites. They're being processed by the neuron. They're going out through the axon. And then you have the synapses that allow neurons to get connected to each other. And this is how the electrical signals flow throughout the network of neurons. And this is what we call a neural net. Now, be prepared. At the level of abstraction, this is going to look something like this, which looks a bit complicated, but it's not. And I'm going to show you in a second why not. The most basic type of neural net we have is what we call a feed-forward neural net. And what that basically means is that the signal, the input signal, is going to travel from the input layer through all the layers in between, all the way up to the output layer. There will be no cycles in there and no loops. And it's very important to remember this. So it's kind of like a one-directional flow network. Makes sense? So from the input, it flows through all the neurons in the net, and then you get the output. Right, so I told you it looks complicated, but it's not that complicated once you read like for a couple of days. So I wanna give you an example of how you can build a 2x3x1 neural net. And by building a 2x3x1, I mean we're gonna have a neural net with 3 layers. We're gonna have 2 neurons on the first layer, 3 on the second, and 1 output neuron. So how do we do this? Like first, we're gonna just create our neuron instances and notice that each neuron has its corresponding bias. And then the rule is that each neuron in one layer has to be connected with all the neurons in the next layer. So we're gonna do this for each neuron in a row. And this is your net. It's like pretty simple, I think. One thing you need to remember is this. First layer is called the input layer. The last layer is going to be the output layer. That's where you're going to find the output of, like the predicted output of your network. Everything in between is called a hidden layer. Make sense? I see nodding heads. I like that. Cool. I'm running late. So once we've done that, we also need to make sure that we initialize the weights. And then so for the input layer, we actually don't need any weights because you need to think of the input neurons as kind of like empty neurons. Like the only thing that they do is they take the input and they just output the same input. It's more of a notational thing rather than a thing in itself. So there's no activation, there's no transformation on the input whatsoever. Right. So then for our second layer, we need to start initializing our weights. So we do that for each neuron. And then the second layer is going to look something like this. And then for the third layer, we have that. And so for the overall net, we're going to have this structure with these parameters. And by parameters, I mean the weights and the biases, because those are going to change. So remember that. Cool. So now that we have the structure, the big question is going to be, because I mean it's all cool and nice that we can draw these things, but then the question is going to be, how does this thing learn? And that's when we get into machine learning. And machine learning is actually really cool, because what it does is, instead of you going and programming, I don't know, like developing a program where you teach the program what it has to do, you're actually going to build a neural net that it's going to, by itself, learn how to come up with the solutions of the problems. And this, I think, is pretty awesome. Cool. You do need to make the differentiation between 2 types of learning. There's supervised and unsupervised learning. With supervised learning, what we're basically doing is we're giving a network a training data set, but we're also giving the net the expected outputs, right? So we're giving it inputs, but also the expected outputs. And the network is going to learn by making its own prediction, and then comparing them to the expected outputs that we fed it. With unsupervised learning, we're just feeding it the inputs, but no outputs. And then the network is going to do all the work by itself, and it's going to start predicting certain things. And the beauty of it, but I haven't gone like super much into this, is that sometimes it can predict like quite crazy stuff. But that's okay. Right, so one basic infamous algorithm for machine learning is backpropagation with gradient descent. I'm not gonna ask you to learn that. You can look at them, like to read that. I'm gonna put the slides on and then you can read it later. But what it basically does is, if you have a feed-forward network, you're gonna feed the inputs through the network all the way to the output. You're gonna have a predicted output. You're gonna compare it with what you were expecting. You're gonna get an error, and what you're gonna do then is you're gonna backpropagate the error all the way back to the input layer, and then you're gonna start updating weights and biases so that the network learns. I'm gonna explain this. So we left off here, yeah, with our network. So let's see how this thing works. We get the inputs, right? So remember that the input layer doesn't do any transformation on the data, so what these two neurons are going to output is what we fed them with, so the X1 and X2 inputs. Next, what we're gonna do is, I should have asked you to take a picture of the first slide. But what we're gonna do now, remember that I told you in the neuron that we're gonna take each weight and each input and its corresponding weight, and we're gonna compute the dot product. So that's exactly what we're gonna do here. So we're gonna multiply these two, we're gonna add them, we're gonna add the bias, then we're gonna wrap this into the activation function, and this neuron is going to output A1. And then what we're gonna do is exactly the same thing for each neuron, right? Cool, so then we have our predicted output, which is great, but then we have our expected output, and most probably, like the first time you're gonna train your net, the predicted and expected output, like the difference between the two of them is not gonna be 0, right? So they're not gonna be the same. And that's what we call a delta. It's going to be the error of our network. And then we start with backpropagating the error. So we're gonna take this delta, and we're gonna backpropagate it all the way back to the input layer. I need to ask this. Did I lose you so far? No? Sure? Cool. Right, so now once that we have all the errors, like this basically calculates the error that is introduced by each neuron in the network, right? And then what we need to do is we need to update the weights and the biases in order to decrease this error, because we want this error to to become 0 if possible. Yeah, I'm not gonna go into that discussion, but that's our aim. So, sorry, the wrong way. So remember that for instance, for this neuron, we have these two weights. Like now with the delta that we calculated, we are going to update these two weights and the bias, and this is going to become this. I'm not gonna give you the math formula because you're gonna hate me for it. So we're gonna do this for every neuron in the net. And then this is our new net configuration. And this is just by running one single item in the training data set. And then the second item that we're gonna pass it through the network, we're gonna start with the network in this state, right? So with the updated weights and biases. And we're gonna do this after every item in the training data set. If you're working with stochastic gradient descent, which means that you're going to update the weights and the biases after each iteration. But you can also do that in batches. So for instance, you can take a batch from your training set, you can feed forward through your network, and then only at the end of the batch will you update the weights and the biases. You want to take these two approaches rather than running your whole training data set and then updating the weights, because then you're going to grow old next to it, because it's going to take a lot of time. Right, so demo. It didn't work before I started on the stage. That's why I look so upset and disoriented, but we can try. So let's do this. What I'm actually showing now is my own implementation of a neural net. It's not the fastest, it's not the fanciest, it's not the craziest one of them all, but it works, or at least it did before it had to show all fancy and nice in front of all of you. but let's try it. So let's create, I know why it didn't work. So let's create a neural net, and I'm gonna, oops. Oh, I have 8 minutes. I need to hurry up. So this is gonna run for a while, but we have candies, so that's okay. And let's help it learn a bit faster. Cool. Let's initialize it to the net that I've been showing you until now. Layers. Let's do this. So we're going to do a 2 by 3 by 1. Yeah, initialize. Spelling is hard sometimes. Then we're going to do, let's see if I still have this. Yes, I do. Cool. Don't try to read that. I'm going to work on this. What I'm teaching my net now is just a XOR operation. So these are, just to explain it quickly because it doesn't look pretty. So it just, for 1, 0 is going to output 1, for 0, 1 is going to output 1, 1, 1, and 0, 0 is going to output 0. So let's run this. Now you can have a cup of tea because it's going to take a while. Not so much, but it's taking its time. But is it clear? Like, does it make sense what I'm doing so far? Like, is this readable enough for everybody? Cool, so it's finished. Now, let's try something. Okay, everybody do a prayer. Let's see, for 0, 0. Yes, it works! Okay, so what this means, like it's not a 0, but it can't output 0 because we have all these crazy weights and biases that are initialized to floating values between 0 and 1. So you don't want to see those values. I did while debugging this thing. Okay, and then if we're going to do this, that's just so that you don't think I'm lying to you. Yeah, okay, this is not a very good number, but it's okay. I was happy. Anyway, trust me, this works. Sometimes you can, I promise you, I ran it so many times. No, but sometimes you can get into combinations of weights and biases that will just either throw your network into a local minimum. Don't ask me what that is now, after. But sometimes your net can just learn slower. It can be slower at learning, or you need to run it in like a larger number of epochs. But it does its thing. Cool. So, right, let's go back to the slides, and then I'm going to show you something else. Let's get into the intelligent Angular apps. We have 5 and 50 more minutes. So I want to talk about weights. Those are very important. And biases, but weights. So the main takeaway that I want you to take from this is that when you're training a neural net, you saw that we're doing all these biases and weights updates, right? And every time we processed another item in our training set, we started from this new state of the net. That's what training it means. It means that we're updating biases and weights. We are slowly shifting them around in order to better model our problem, right? So this is really the main takeaway. When you're training a neural net, at least by my reading so far, you're updating weights and biases. That's it. That's all. And this is actually, this is cool to understand because this opens up a lot of possibilities for us. So when we're talking about neural nets in web apps, for instance, we get tons of possibilities. Like, for instance, what could you do? So you could have a net running in the cloud, right? And then you can train it and train it because you need a lot of computational power. And then cloud services provide that. And you can train it in the cloud and then take a snapshot once that net is trained. And then you can port it in your application. And then you start with a ready trained net, right? Does that make sense? You still follow? I didn't lose you? Awesome, cool. And I didn't even bring candies. Oh. The other thing you could do is, you could run your own implementation, right? Like I did, for instance. And that's well, for that you kind of need to understand a lot of stuff and you need to make it performant and so on. So that might not be the solution you want, but you could still do it and you could train it by yourself and then still start with a ready trained net. Another thing you could do is you could use current implementations like TensorFlow or Keras or ConvNet.js or Brain.js. And these are all like quite sturdy solutions. And they give you a lot of possibilities into how you can train these things. And they also give you possibilities of, for instance, taking snapshots of them and then shifting them around. And that's actually, for instance, I'm not sure if it's the Google Photos app or I'm not exactly sure which one, but it's one of them that does exactly that. So it has a net that's been trained somewhere else, and then it takes a snapshot of that net, and it ports it into your mobile device, and then when you're using it, it's still learning, but it starts from a pre-learning, like from a predefined state, right? So it doesn't start from scratch. It doesn't start from zero. 240 minutes. Okay, I think I can still show you. So with that in mind, let's see. Snapshot. Yes, okay. So if I'm going to do net2, which is going to be a new neural net with the defaults, and then dot initialize. Oh man. So let's see. Can somebody tell me which one this is? We're the 27th today, right? Okay, so I'm not going to write this. I have 152 minutes. But the idea is that I've implemented in this net the possibility to take a snapshot. And then it saves all these snapshots as a JSON file. And you can see them here like this. So you see that there's just, it's exactly the configuration of my net. So it shows you the layers that it has. And then for each layer, it shows you the nodes, the number of nodes and their configuration in the net. And this is pretty cool because, for instance, I can just take this net, I can train it somewhere else, and then in my application, I can just use it as is, like already pre-trained. I can show you this afterwards when I'm not running out of time. Like, just come and pick me up somewhere here, and I can show you. I can run it for you. Yeah? Is that okay with everybody? Am I not going to be thrown tomatoes at? No? Okay, cool. So then I can try. Yeah. Okay. Cool. So let me see Command T. Can somebody tell me does anybody know by heart the command line for displaying the full path of a file? What? E? P? W? D? And then? Okay. So let's see. Node module snapshots. Yeah. Okay. Yeah, but I want, let's see. Right. Sorry? Which? So, now? Now what? No, never mind. I'll manage. Here. So, let's see, initialize snapshot. And then it was this one. Sorry, yeah. Of course. Yes, yep, saw it. Okay, so net2.predict. Let's see if it's, okay. Cool, yeah, right? It's kind of the same number, almost exactly the same number. I didn't cheat, it actually works. But yeah, so I think this is pretty powerful. I really think this is very, very powerful, and it opens up a lot of possibilities. I want to give a shout out and big thank you to these three very nice gentlemen. Well, two gentlemen and the cat on the left-hand side, but I know you're a gentleman. They really helped me a lot with this talk, and thank you very much for them. And thank you very much to you. Thank you.